Yeah, if it's our physics textbook, it's a no.
Starbucks
All right, let me get started. I will begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for this class, this opportunity we have to meet and study your creation. Just pray that you'd be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. So, hope you guys had a good break. Here's the attendance sheet. I have not made the corrections to the grades yet on the previous test. So if you don't see it there, that's because I haven't done it. And you're not alone. I just haven't done it for anybody yet. So sorry about that. I was about an hour ago, and then something distracted me. I don't know what it was. So I want to talk about collisions today, and so let's get into it. What's a collision? Right? Yeah. So yeah, typically collision is when you have two or more masses slammed together, right? They collide and then they come apart, right? Or they stick together, and this is a collision. Now the collisions, elastic or inelastic. What does it mean? Elastic. Elastic means that the kinetic energy before the collision is equal to the kinetic energy after the collision. Inelastic means that the kinetic energy before the collision is not equal to the kinetic energy after the collision. So elastic collisions are especially special. They're very nice. And there are special things that hold. Like a theorem we worked out last time is for one-dimensional collision between MA with VAI and MB with VBI, producing after the fact, VAF for MA and VBF for MB. All right, so I'm saying that the velocity before the collision is VAI. The velocity after the collision is VAF for mass A. I'm saying before the collision, the velocity of VB is VBI. After the collision, the velocity of VB is VBF. That's my notation, okay? Then here's the punchline. If the collision is elastic, then VBF minus VAF is equal to minus VBI minus VAI. All right? And in fact, this is a biconditional. It's if and only if. Like, the only way that the collision can be elastic is if this condition is met, in fact. So, I could like say collision is elastic if and only if this condition's met, all right? That's the content of the calculation we did. I took my time getting to it, right? It took us a while to derive that. It's actually kind of a pain. It's quite a pain to derive that, and unless you have your ducks in a row, so to speak. But this is a super convenient condition for one-dimensional collisions. You can easily ascertain whether or not they're elastic by simply checking this condition. And this condition is much easier than the direct checking of kinetic energy, because kinetic energy is quadratic in the velocity, whereas this is straight up linear. So for example, suppose we have, let's see here, let's stick with my example here. So I've got MA equal to, let's say, 2 kilograms. And over here, I've got MB equals to 4 kilograms. All right. And let us suppose that this one is originally 10 meters per second. All right. And then I usually draw two pictures. Here's the collision. So this is before, and over here is after. So after, I have MA sitting here, and VAF, let's suppose it's 0, and MB, we've got VBF. Okay? So my question is, given all this, and by the way, so here this one's at rest. So just to finish my storytelling here, so what we're looking at is like VAI is 10 meters per second. VBI, in my current language, is 0. VAF is 0. VBF is, I don't know. I don't know what it is. All right, so let's say that's the question. So I have a twofold question to ask. The question is, what does the velocity of B have to be after the collision? And question number 2, was this collision elastic? All right, so let's work it out. How do we find VBF? What principle do we use? Kinetic energy, nope, we don't know that. In a collision, kinetic energy may or may not be conserved, but what momentum is conserved, right? So we conserve momentum. So that gives us MAVAI plus MBVBI equals MAVAF plus MBVBF. This is one-dimensional, so we just use the sign plus or minus to indicate right or left direction, okay? I don't try to, as a matter of typical setup, try to decide whether they're pointing left or right afterwards, because it just begs confusion. So instead, just let the math do the work for you. Leave it as VBF. If it's going to the right, then it'll be positive, and if it's going to the left, it'll be negative. The math will tell us. All right, so like, all right, so VAI was 10. VBI is 0. VAF is given to be 0. And so we're trying to solve for this. So VBF equals 2. MA times VAI divided by MB, apparently. Which is, what you got here? You got 2 kilograms times 10 meters per second divided by 4 kilograms. Looks like VBF equals 2. 20 divided by 4, so 5 meters per second. So there's the answer to the first question I posed, which was what was the velocity of the second mass? Now my question to you is this an elastic collision? Yeah.
So momentum is conserved even if kinetic energy is not?
Momentum is conserved, yes. As long as the collision happens in an instant, such that there's not enough time for external forces to change the momentum of the system, the conservation of momentum is inescapable. On the other hand, like you could even have ice skaters as a like a less than instantaneous thing, right? If you had 2 ice skaters in an ice rink, the ice rink is essentially frictionless, give or take, ignoring the fact that the ice skaters, of course, push off the ice to make themselves go. Let's forget about that. Imagine a world where ice skaters are hopeless. They just drift across the ice aimlessly, and they hit into each other. Then if, after they collide, momentum would be conserved even over a period of seconds if there's no force external to the two ice skaters, right? So if the net force on the system is 0, the change in momentum is 0. That's the math. But certainly in an instant we have momentum conservation. So I saw one of you say, no, this is not elastic. So if you believe my theorem, what do you check? What's the relative? So this is relative velocity. See this? So what we're looking at here, I would say this is the relative velocity between A and B, right? If you can imagine, so the relative velocity between A and B is this. So VBI minus VAI is what? Excuse me. So that was 0 minus 10, which is minus 10, minus 10. So this is 10 meters per second. If I do the minus, I get a plus, right? But what is VBF minus VAF here? It's just equal to 5 meters per second, right? Because it's 5 minus 0, which is 5. 5 is not equal to 10. I think we can agree, right? So therefore, not elastic. Now, if that doesn't convince you, we could directly calculate the kinetic energy before and after, right? Let's verify it. Let's verify my theorem in the context of this example. What is the initial kinetic energy? So let's verify the inelasticity of the collision. Sorry, I tried. So KEI, 1/2 MA V naught squared, right? There's no kinetic energy for VB, right? So that doesn't matter. It's got 0 kinetic energy. And so that's 1/2 times 2 kilograms times 10 meters per second squared, which is giving me 100 joules. On the other hand, KEF is 1/2 MA VAF squared plus 1/2 MB VBF squared, right? So when we talk about kinetic energy, we're talking about the kinetic energy of the system. This marker's dead to me. It's close. All right. Well. So sadly, well, or not sadly. So one of these is 0 by assumption. I told us. I assumed in this problem. I said VAF was given to be 0. So this is given to be 0. And what do you got here? Well, you got 1/2. 4 kilograms times 5 meters per second squared. That's 25 times 2. That's 50 joules. As you can see, we lost 50 joules in this collision, right? It's an inelastic collision. So here's my question for you guys. Given this starting point, what has to happen afterwards in order for this to be an elastic collision? Yeah.
Friction?
No friction.
It has to be equal.
Has to be equal. Was that what you're saying?
I was going to say mass A has to go in the opposite direction for equal velocity, or equal energy.
These are all interesting suggestions. Unfortunately, they're all wrong. Your heart is in the right place. You're absolutely right. They both have to be moving, but they don't have to be moving with equal velocities, as it turns out. Yeah.
They have to be like moving together, stick together after collision.
No, that would almost certainly be not elastic. Whenever they stick together, it's going to be inelastic. It's just as far as I know of, all sticky collisions are inelastic. Listen, so I don't think I could guess it if I was in your place either. You have to work it out. So to work it out, so let's state the question. So forget VAF equals to 0. All right. What VAF and VBF must be given in order for the collision to be elastic. Let me say it a different way. If the collision's elastic, what do the final velocities have to be? Right? That's the question I'm asking. Okay? So if you do this directly by saying, well, the kinetic energy before has to be equal to the kinetic energy after, that would be a bad decision. Because what you're sentencing yourself then to is all of the algebra we did to prove that theorem in the context of this example. You don't want to do that. So what you want to do is use the theorem and momentum conservation. So we have two things. We have that VBF minus VAF, right, is equal to 10 meters per second, all right? That's by the relative velocity theorem. Let's give this theorem a name. Let's call it the relative velocity theorem, all right? Only good for elastic collisions. But we also know this up here, right? We also know that 2 kilograms times 10 meters per second is equal to 2 kilograms times VAF, which we don't know, plus 4 kilograms times VBF, which we also don't know. But now we should be happy. Let's omit units. Omit units to make the algebra less annoying. So we've got like VBF is equal to 10 plus VAF, right? And we also have that 20 is equal to 2 VAF plus 4 BVF. And at this point, you guys should be like, oh, well, that's not too bad. I can solve that, right? That's 2 equations, 2 unknowns. We can work through that. How would you suggest we do it? Substitution? Sure, I like that. So this offending VBF here, I'm going to put these guys right there. And that'll give me 20 is 2 VAF plus 4 times 10 plus VAF by that substitution, which then gives me 6 times the final A velocity is equal to 20 minus 40, also known as minus 20. So therefore VAF is minus 20 over 6. Putting the units back in, we have VAF is equal to minus 3.333 meters per second. And what's VBF? Well, VBF, 10 plus VAF. So that makes that 6.666 meters per second, approximately, of course. It's an unending decimal, truth be told. There you go, that's what has to happen. Now, if one of you said that and I didn't hear it, my apologies, all right? But I think I heard you guys saying they had to be equal. The velocities had to be equal. That's not the case, right? The difference in the masses comes into play here. But you're right that the energy has to be shared between the masses. That's true. And check it out now, right? If you calculate 1/2 MA VAF squared plus 1/2 MB VBF squared, what do we think we're going to get? What do you think we're going to get? So that gives you like 3.33 squared. Times a kilogram, and then plus like 2 kilograms times 6.666666 meters per second squared, and guess what? That's 100 joules. Elastic collisions are very special. Most collisions are not elastic, all right? It's like, I don't know, like a perfect game in baseball or something. I mean, it just doesn't happen that much. Well, that's not true. I mean, there are a lot of elastic collisions, actually, theoretically speaking. But elastic collisions have a very particular signal. They're very, very particular. Like most of the collisions are not elastic. All right. Any questions? Do you guys? I hope you see what I'm saying here. For one-dimensional problems, if you are given that the one-dimensional problem is elastic, it is important to use the theorem to solve these, because otherwise you have to solve a quadratic equation in the velocities paired with the linear equation from the momentum conservation. And the algebra of that is just ugly. All right? So way easier to use the theorem. I know this because I have tried to solve these problems without using the theorem, and I usually can do it, but at the end of it all I regret it because I remember, oh, you idiot, you have a general result, you should use it, you know? The idiot is me, just to be clear. You're like, we already knew that. So rude. So rude. Let's see here. All right, so this is the other one thing I should emphasize. This was all one-dimensional. This is all one-dimensional. What happens when we bump it up to 2 dimensions? Vectors. Very good, yes. So let us begin the 2-dimensional problem. Now, I should, full confession. I tried to derive what I'm about to try to derive before class, and I couldn't get it. So, but you guys are going to help me. Whatever mistake I was making before class, we're not going to make now. We're going to do it together. And you guys are going to keep me from making that mistake. So we're going to figure it out. What's that? Now, here, this is, this example I'm about to show you is a problem that Dr. Skambordis would oftentimes put on a test. Oh, yeah. I myself have put this problem on tests. And it is straightforward, but it does require a certain amount of algebra to get through. So let's see if we can do it. But the ingredients are pretty simple. So here's the setup. We have MB sitting at rest. Without loss of generality, we're going to say that MA is over here, and it has velocity v naught. And we're going to assume, because this is physics, and we can make the coordinate system whatever we like. So when you're given a problem, as physics students, you can engage in this practice. Choose a system of coordinates which makes your life easier. The way to make our life easiest here is to make the initial velocity of A to be in the x direction, because then that sets up a coordinate system which is relatively easy to understand. We're going to then assume that there is an elastic collision. All right? And we're going to assume that it's not quite dead on. All right? It's not quite dead on. If it was dead on, right? If it just hit it smack on, right? Then the problem would just be one-dimensional. We'd be back where we were already talking about. All right? So we want it to be like a glancing collision. Okay? So afterwards, continuing on the line which A was originally traveling, let's make the line here. All right? We have, without loss of generality, I'll put MA up here with VAF, and stemming from the collision point of there, say the collision point was here, fine, whatever. Don't make too much of this picture. And then down here, I have MB with VBF. These are, as you guys told me, vectors. Very good. And so we can characterize those by an angle alpha and an angle beta. All right? So the question is simply this. What is the sum of the angles after the collision? That's the question I ask. Question. Alpha plus beta equals to what? That's the question. All right? So if you see this on a physics test, it's a somewhat terrifying question if you've not tried to work it before, because it feels like you're given almost nothing, right? All you're given is that one of the things is at rest and the other one has velocity v naught in the x direction, right? How can you possibly hope to solve this problem? Well, I couldn't an hour ago. I hope it turns out better right now. Otherwise, the rest of my day is going to suck. It's just going to be horrible. All right, so elastic. So we have two things. The one thing we have is that MA, VAF, excuse me, MA, start this out right. MA, V naught, 0, right, is equal to MA, VAF. What's VAF? Well, VAF is VA cos alpha, VA sine alpha. That's the momentum of A. What's the momentum of B? Well, in the setup that I have chosen here, you got yourself VB cos beta, and careful, it's going down, right? So we must put a minus VB sine theta there, right? Sine beta, rather. So this is momentum conservation, right? So let's do what we can with these equations before we go on. So I've got like MV naught is equal to MA VA cos alpha plus MB VB cos beta, right? I know that. What else do I know? I know that 0 is equal to, let's see here, MA VA sine alpha minus MB VB sine beta. All right. And that's not, first of all, come on guys, don't let me do this. What am I missing here?
A.
That's an A, right, MA. So, all right, I think I'm just going to leave those like that and resist the urge to do anything else to them. I'm just going to leave them like that. Maybe I'll see something better than I saw before class, because before class I did stuff at this point, but it didn't work out. So now I know that I made an algebra mistake before class because I know this problem is solvable because I've solved it before, at least like 5 times in my life. Because I do this every single time I teach physics. But I also don't seem to have it in my notes, which is annoying. Hey, I was typing up more notes for you guys. I'm not done yet, though. So there will be some new notes coming out sometime somewhat soon. But it's mostly stuff I've already lectured in class, so my apologies. But all right, so that's the first thing. Momentum is conserved. What else? We also know that we have, kinetic energy before, which is what? 1/2 MA V naught squared, right? Is equal to what? 1/2 MB VB VB squared. I'm sorry, I'm going to use the A first here. 1/2 MA VA squared, right? Plus what? 1/2 MB VB squared, right? So this is the kinetic energy before, that's the kinetic energy after. These also have to be equal. All right? I feel relatively confident that I should rewrite this as like MA V naught squared plus, equal to MA VA squared plus MB VB squared. All right. So we've got some equations that we need to somehow solve, right? So we'd like to eliminate a variable. Yeah? I guess you could go different ways. I think I usually eliminate V naught. That just to me looks natural here. So V naught squared is VA squared plus MB over MA VB squared. See that? I just divide by MA to get that. I can do that, right? On the other side, on the flip side of things, from this right here, I also can get that this is equal to, V naught is equal to VA cos alpha plus MB over MA VB cos beta. So that's another formula for V naught. Now, in order to eliminate V naught, I need to take, let me call this equation star, square it, right? This is equal to the star equation squared, which in this case would be what? Like VA cos alpha plus MB over MA. And I'm just writing it out in gory detail because I know I've got a tendency to make mistakes somewhere here. My mistake's usually in whatever I don't write down, personally. All right. So then what? So we should FOIL this thing out, right? So I've got VA squared cosine squared alpha, excuse me, plus 2 times MB VA VB divided by MA cos beta cos alpha plus MB over MA quantity squared VB squared cosine squared beta. All right. So I'm not sure what's the exact right step here, but what I'm going to do is I'm going to take this equation that we just found, and I'm going to put it all to the what's this direction? Left, all to the left. All right, so basically take all of this and put it over there. So I have VA squared, and I've got a 1 minus cosine squared alpha. All right. And then I've got my minus 2 MB VA VB over MA cos beta cos alpha term. And then I've got myself plus parentheses MB over MA minus MB over MA squared. Oh, rats. All right, let me try that again. MB, I bet that's where I made my mistake. MB over MA times 1 minus MB over MA cosine squared beta VB squared. Again, I'm moving everything over to the left-hand side. So like when I factored a VA squared out, so like these two, this term and this term become that term. The middle term I just subtract. And then over here I'm factoring out a MB over VB and a VB squared. So that puts the 1 from this one here. But on the other side, I have 1 copy of MB over MA. I've got a VB squared, but I also got a cosine squared. So I'm pulling out 1 copy of these and the VB squared to the outside. That leaves me with an MB over MA and a cosine squared beta there. All right. Meh. Okay, then what? What have we not used? We didn't yet use the y component of momentum conservation. See, and this is an interesting equation because it gives us hope. Like when you first work this problem, you just want to yell, I need to know something about the masses. The masses have to be equal. If the masses were equal, everything would be wonderful, right? But they're not necessarily, I don't believe. So here, I mean, here we have what? We've got MA, VA, sine alpha equals to MB, VB, sine beta, right? So solve that for, let's see, I'd like to solve that for like MB over MA, I guess. What's that give me? I think I'd have a VA sine alpha over VB sine beta. And you see, well, if you guys think I'm wrong about this, let me know, because like, it's at least dimensionally consistent. Everything's got a squared velocity. The masses are canceling, so that's dimensionless. What's that? Oh.
Is it 1 minus sine instead of 1 minus cosine of the
Oh, this one?
Yeah.
I mean, you can trade that for a sine squared. I mean, it is true that that simplifies to sine squared alpha. That is true. But not yet. The real issue over here is, okay, so the MB over MA is what? See this right here? So let me write that again closer to what we're going to use it. We have MB over MA is equal to VA sine alpha over VB sine beta, right? So that equation allows you to trade ratios of masses for trigonometric functions and velocities. That means we can remove masses from this equation by using that. See? So this is really VA squared sine squared alpha minus, let me just put the 2 VA, let me write it this way, minus 2 VA cos beta cos alpha. And MB over MA is really what? VA sine alpha over VB sine beta. All right, so that's the middle term. And then we've got ourselves a VA sine alpha over VB sine beta. And what's that?
Do we need another VB on that second term here in the 2 VA? That'd be 2 VA PV?
2 VA VB, VA BB. Yes, thank you. Excellent. Indeed, they're still there. So now I've got, that's my MB over MA. Now I've got 1 minus MB over MA, which is again VA sine alpha over BB sine beta times the cosine squared of beta. Great. And then you got your VB squared out here. We hate fractions, right? Agreed? How can you make the fractions go away? Let's see here. What if I... Well, this probably can be simplified, but let me just multiply the whole thing by sine squared beta. If I multiply by sine squared beta, I have, and I probably need to multiply by VB squared sine squared beta if I had to guess. What's that? What?
What are the odds we're like still on the right track?
Pretty good. They're pretty good. So, all right, so I'm sorry?
Are we allowed to just multiply by VB?
Yeah, you could multiply. I mean, if VB is 0, you can easily derive a contradiction. It has to be non-zero.
Or will we have to? Because that's not multiplying by 1.
We can multiply an equation by a non-zero quantity. That's allowed.
Okay, so both sides are.
Yeah. So that, and then what happens over here? Minus 2 VA VA squared VB squared. And when I multiply by the sine squared, so notice I'm canceling these VBs before I do the multiplication, okay guys? Cancel those, multiply, you get a VB squared. But the sine beta and the sine squared beta leaves you just a sine beta. So you've got cosine beta, cosine alpha, sine beta. All right, that's the middle term. The next term, I'm multiplying by VB sine beta, right? So we've got VA sine alpha times, and then I'm just going to use one of those copies in here. So I've got VB sine beta minus VA. Oh, sorry, I lost my track. Son of a gun. Just a second.
Oh no.
So I'm trying to multiply this one here by VB. Maybe I should just write it out. Let me just write it out. So I've got VB sine squared, VB squared sine squared beta times VA sine alpha over VB sine beta. Maybe it's in our best interest to make a common denominator there, yeah? So we've got VB sine beta minus VA sine alpha cosine squared beta divided by VB sine beta VB squared. 0. So, oh, hey, look at that.
There's too much to look at.
No, 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 no.
I am of you. I just did the right thing. Yes.
Have ye no faith? Look.
My feet is Oh, whoa. Bye-bye. Bye-bye.
So that leaves me with those cancel. And this right here then gives me, I'm not going to get back up from this. All right, VA, VB, sine alpha, sine beta, minus, goodness gracious, VA, VA squared. Oh, there's a VB squared out. Oh, man. Why'd I do that? VA, there's got to be an easier way to do the math here. Anyway, sine squared alpha.
Sir,
Cosine squared beta. All of that times VB squared.
Hey, at least the stuff in the front can be subtracted. There's a VA squared, VB squared.
This should simplify down to like, no, this whole term should simplify down to VA squared, VB squared, cosine squared alpha, cosine squared beta. That should be what we see from this.
Whoever. God.
Yeah. All right. Well, somehow that collapses to this, and so what we have is VA squared, VB squared times that. There's a VA squared, VB squared, and everything, and what you have is a sine squared alpha, sine squared beta. Minus 2 times sine alpha, sine beta, cos alpha, cos beta, and then plus cosine squared alpha, cosine squared beta, which can be factored, if I did this right, to sine alpha, sine beta, minus cosine alpha, cosine beta, quantity squared. Now the other possibility is I'm remembering the problem wrong. We do need to know the masses are equal. So, but I don't think so. I think the masses don't have to be equal. So assuming that I'm just not able to, so I was hoping you guys would find it for me in the midst of this. Anybody? No one's seen my algebra mistake here? Maybe there's not a mistake. Maybe this actually does simplify like I'm hoping it does and I just don't see it.
I say yeah.
You guys start snickering and like doubting and stuff and that like bleeds into my brain and makes me worse. So.
Our edges are not wide enough for this.
All right. You need art tablet? Yeah.
No, I refuse.
So, punchline. So I'm pretty sure that this does actually work out to this if I don't make a mistake somewhere. And so this is what?
Sine x plus 1 or no.
This is sine of alpha. Wait a minute, is that sine? Oh, I should trade this for cos alpha, cos beta, minus sine alpha, sine beta, right? If I did that, you should recognize that that is the cosine of alpha plus beta. So we need that that's 0. So what's the answer to the question?
Sine.
What does the sum of the angles have to be?
Sine.
90 degrees. Right.
There's no way. That was my original. That was it. It was 90 degrees.
So try it out. Try it on the pool table. What happens if you hit a ball like glancingly? Yeah.
If you ask us on a test and we just guess it is 90 degrees, we give credit.
No. I mean, I'll give partial credit, but
How much
do we have to show?
I think the easy way for me to make this problem like infinitely easier on the test is just to give you the masses are equal. Then all of a sudden the algebra, like, if the masses are equal, this all becomes much easier. Yeah. Yeah.
That means that would
Mm-hmm.
because something like this would apply to when the masses are equal anyway, why not just solve for when the masses are equal?
Because then we'd only know that it's true when the masses are equal. But, I mean,
But you told us that it's also true when the masses aren't equal, so we know that it's always true.
I could be wrong about this being true when the masses are not equal. Maybe that's why I can't do the math. Right? Maybe. Maybe there's some impasse here.
Google it.
Google it.
Use your textbooks for once.
Well, I will say this about Google. Like, I was trying to buy like non-GMO cookies at Walmart in break. We've got a minute, so I was trying to buy non-GMO cookies at Walmart, and so then I just started looking. Every single stupid box of cookies at Walmart, it's like bioengineered ingredients. And my mom has said various negative stuff about bioengineered ingredients, so I thought, oh no. And I've heard this story about how they, basically manufacture plants to basically have their own pesticide. But because the plant has the pesticide in the food, you don't get in trouble because the government only regulates adding pesticide chemicals, not putting the chemicals actually de facto into the food, right? Makes sense. So I thought, well, maybe I'm wrong. Maybe the bioengineered food is fine. So I thought I'm going to start researching this. I'm going to start looking for articles. And what I found was that every article that Google gives me says that bioengineered foods are fine. They're all great. All scientists agree.
Yeah, they taste pretty good.
I read, and so I said, well, if scientists say it's true, and all of them say it's true, and there seems to be no debate on the topic whatsoever, according to Google, it must be fine. So what am I worried about, right? Trust the science, right? It's worked out really well for us lately. Yeah, sorry, there's a mistake here somewhere. Probably.
I thought you were going to have a